Hey guys, the objective of this video is to introduce you to Coulombs Method. We're going to be looking at the undrained for active and passive force diagram for Coulombs Method. We're going to be, from that diagram, being able to find the weight, the cohesion on the wall, and the cohesion on the soil. We're then going to draw the vector force polygon to scale, and then we're going to find the total force on a wall. So we're not going to actually do any numerical examples. This is just going to introduce you to all the process and the formulas. So first of all, Coulombs method. So in the previous video we saw Rankine's method for a retaining wall. So we had a wall and we converted vertical forces to horizontal stresses. So vertical stress to a horizontal stress. Now in Coulombs method it's a little bit better because what we do is we can analyze a failure plane. So instead of going from vertical to horizontal, we analyze a plane, a failure plane, so at an angle. So we analyze this plane and how it fails. The benefit of Coulombs method compared to Rankine's method is that we can deal with any geometry. So say for example we had more of a slope like this on our wall which went up, we'd be able to consider that slope, where in Rankine's method we wouldn't be able to. We can also consider friction between wall and soil, which we couldn't do in Rankine's method. So we can consider friction along the wall and soil interface, which would develop. So just in this video we're going to be looking at the undrained formulas. So for undrained, which is obviously a total stress analysis, we're going to be looking at the parameters phi u and cu, so there's the undrained parameters, but also we need to have these new parameters, which is phi of the wall and c, the cohesion of the wall. So we've just got undrained parameters where we're using phi w and cw as well included in our undrained total stress analysis. So now what I'm going to do is we're going to analyze this failure plane. So we assume that, so let's first do the active failure. So active failure, we know that is a minimum failure. And we know that is when the soil falls on the wall. Okay, so the active failure is a minimum failure where the soil falls on the wall. If I were to draw a wedge of this, so this is our failure plane. So here is, so in the wall, this is the soil that's failing. Okay, so we're failing along this plane. So we call this angle theta. That's the angle we're failing at. Now what I'm going to draw in, all the forces we have in this failure plane. So we're going to call that A, B, and C. So the first force we have, so a good thing to do first of all is to draw the direction of the soil. So because the soil falls on the wall, the soil is moving in this direction. So the soil is moving down. So we call that soil movement. Okay, the soil movement is going this way. And that will now allow us to draw in all the reaction forces. So the first force we're going to have is obviously just the weight of this wedge. So we have weight of the wedge. We also have the cohesion of the soil. Because the soil is moving this direction, we're going to get friction force from cohesion. So this way, a cohesion of the soil, C subscript S. We also have a normal force acting on this, which, as we saw in some of the previous videos, this is at an oblique angle of the friction angle. And this friction angle, so this we will call the reaction of the soil, and this is at a friction angle of phi subscript u, so the undrained friction angle of the soil. Now on the wall we also have other forces happening. We have, if the soil is moving down, we have a reaction force going up, which is the cohesion of the wall. And then also we have a normal force, which is also at an oblique angle. So we'll call this the R of W, so the reaction of the wall. And that is at an oblique angle of phi W. So that would be a diagram of all the forces we have for an active failure case. Now we can also have a passive failure, so it's going to be the exact same diagram except everything is just the opposite. So passive failure is a maximum failure, and we know that occurs when the wall falls on the soil. So if I were to draw this, so we'd call this A, B, C, but this time the soil is moving in this direction because the wall is falling on soil. So soil movement. Now we draw in all our forces. So the weight force is still going down. That's the weight force. We'll be at theta. So theta is the angle of failure. Theta equals failure angle, or the failure angle of the plane. So it's the failure angle of the plane we're looking at. Now, because the soil is moving this way, we're going to get a friction force or cohesion force going this way, which will be CS. So you can see it's the opposite of that direction. And similarly, the reaction force will also be at an oblique angle. So RS, the reaction of the soil, which is at an oblique angle of phi U. So the undrained friction angle. And also we have, because the soil is moving up, we're going to have a friction force going down, so the cohesion of the wall. And still, let me just put that there, cohesion of the wall, we have a reaction of the wall, which is at a oblique angle of phi wall. Okay, so that is our diagrams for the active and passive failure case. You can just see the easy way to do it is just remember soil falls on wall, which means the soil movement is this way, and you can just get all your forces like that. It's all the reaction forces. And for a passive failure, a wall falls on the soil, so the soil is going to go up this direction as the wall falls. So the wall is going to fall on our soil, which is going to push the soil up that way, which means that you can easily determine all the reaction forces. So instead of remembering what these diagrams look like, just remember soil falls on wall, soil moves down. So wall falls on soil, soil moves up, and you can draw in all the reaction forces based on that. I'm just quickly going to show you how to find W, CW, and CS. So W, CW, and CS, we can find that just from our diagram. And then I'm actually going to split this video into two parts, and we're going to be looking at drawing the vector force diagram, vector force polygon to scale in the next video. So we can find W, which was the weight force. So we have W, the weight force will just equal the gamma of the soil times the area of triangle ABC. So that's all we do to find the weight force. We just times the gamma of the soil by the area of triangle ABC. Same thing for the active and passive case. So that's how you find the weight force. To find the CS, so the cohesion of the soil, so CS, that term there, and similarly that term there, you would just go C of the undrained, so C subscript U for the soil, so C subscript U, times by the length it's acting over, so times by the length BC, and similarly times by the length BC to get CS. To get CS, you times the C subscript U, which will be given to you in the question, times by the length it's acting over, which was BC. Similarly, to find C of the wall, you would be given C of the wall. So this is capital C subscript W, and this is little c subscript W. So these two values will be given to you. So Cu might equal 6, Cw might equal 5. They'll just be values given to you. And then to find the force, it would be little c subscript W multiplied by the length it's acting over. So in this case, Cw acts over AB. Similarly, Cw acts over AB for both the passive and active case. So this would be multiplied by AB. So when you do these questions, the first thing you're going to do is draw your diagram, and then you can quickly find the actual forces. And these will all be in kilonewtons per meter. Alright guys, I'm going to split this video up into two parts as I said. Watch the next part to find how to know how to draw the vector force polygon, and then also to find the total force acting on the wall. So we'll see you in the next video.